Our goal for this lab is to experimentally determine how much excess charge is on one piece of charged clear tape. In the first lab, we learned that ordinary objects can acquire an excess or deficiency of negative charge if they are rubbed, pulled apart, or touch each other. By using this logic, we were able to conduct an experiment to determine the amount of excess charge that is on one piece of charged clear tape. Before we do anything, we need to make an estimate of how many valence electrons there are in the tape. First, we established a lower and upper bound. We determined our lower bound to be 1 electron and our upper bound to be 4.8 millicoulombs, and estimated there are 3 times 10 to the 16th valence electrons on a piece of tape. We drew a free body diagram for the piece of tape when it is suspended in the air to determine what forces are acting on it. Those forces are a weight force, and when another piece of charged tape is brought near, there is an electric force. This allows us to create a net force equation to help determine the charge. The equation we found is Q equals square root of d squared times mg over k. Before we conducted the experiment, we made some assumptions since we only needed an approximate answer. The charge on both pieces of tape are the same. The charge on each piece of tape is not spread out over its surface, but instead is concentrated at a single point in the center of the tape. The experiment takes place near Earth's surface, so acceleration due to gravity can be approximated as g, and the supports exert no force on tape B once it begins to float.
To conduct the experiment, we charged a piece of tape on the base tape, then stuck it to the side of the table. We checked to see if it was charged by using a group member's hand. Since they were attracted to each other, the tape was charged. This is because her skin cells were polarized by the charge on the tape.
To ensure that both pieces of tape were the same charge, we charged both pieces of tape by placing them on the base tape and ripping them off and put them near each other to ensure they were charged. Because we are assuming they are the same charge, we predicted that they would repel, which they did. Out of curiosity, we wanted to determine if the tape had a positive or negative charge. To do this, we charged the tape and used a balloon that had been charged by rubbing it up against one of our group members' hair, and put the tape and balloon in close proximity. Since we know balloons are negative, if the tape is positive, then they will attract, and if the tape is negative, they will repel. When we did this, the two are attracted, meaning that the tape is positive since we know that the balloon is negative. In order to cause one of the pieces of tape to float, we charged one of the pieces of tape, tape A, and held it parallel to the two stacks of DVDs, our supports. Then charged another piece of tape, tape B, and placed it on the supports. We then moved the bottom piece close to the top piece and observed the top piece repelling or floating. We also held a ruler next to the tape so we could measure the distance that the top piece was repelled. When analyzing how this experiment works, we can determine through Newton's second law that there's a weight force, but also an electric force that is acting on tape B when it is floating. While conducting the experiment, we had a difficult time getting the experiment to consecutively work. We learned that this is because the base tape can become oversaturated by preventing tape A or B from becoming charged. First, we had to determine the gravitational force on tape B. We measured the piece of tape and found that it was 21 centimeters or 0.0021 meters and had a mass of 0.168 grams. We used Newton's second law, or mass times gravity, and found that the gravitational force on tape to be 0.0016464 newtons. The distance of separation that we measured when causing the tape to float was about 3 centimeters or 0.03 meters. We then used this distance, mass, gravity, and K, and put these amounts into the formula Q equals square root mg d squared over K to get the charge of 1.3 times 10 to the negative 8th coulombs. In order to find the charge, we had to make the assumptions that the atoms are in a two-dimensional shape and that they are in a lattice format. Using the gravitational force, we were able to determine that there was a deficiency of 8.125 times 10 to the 10th electrons. In order to compute the ratio of electrons to atoms, we needed to make the assumption that not every atom loses electrons. We were able to find that there are approximately 8.125 times 10 to the 16th total atoms on the piece of tape. This allowed us to determine that there is a ratio of 8.125 times 10 to the 10th to 8.925 times 10 to the 16th, or 9.1 times 10 to the negative 5th percent of electrons into the number of atoms, meaning that the tape is electron deficient, meaning that it is positive. From this experiment, we have a better understanding of how charges work on everyday objects.